Right, in this example, we're going to solve the following problem. We have a fish manager that knows their fish population naturally increases at a rate of 1.5% per month. At the end of each month, 120 fish are harvested, and we want to know what's going to be the long run or steady state population, if there is one, of the fish. Okay, so that's our goal, and we're going to let f sub n denote the number of fish after the nth month. We're going to assume that they're starting out stocking with 4,000 fish, right? And we're going to figure a formula out for this sequence and then use that formula to determine the long run behavior. Now, I've got a graph of the sequence listed below, but I just want to look at the recursion formula that we're going to be using here. So we're going to increase the number of fish by 1.5% per each month. To increase a quantity by 1.5%, that's equivalent to multiplying it by 1.015, because you're adding on 1.5% to what you had started with. So that's like being left with 101.5%. Right? In general, if you're taking a quantity and multiplying a given amount by 1 plus r, you will increase it by r percent. If you take a quantity, say a, and you multiply it by 1 minus r, you'll decrease that amount by r percent. All right, so after the first month, we're going to have 1.015 times the original amount minus 120. In general, your fish population in any given month is going to be the previous population increased by 1.5%, which is like multiplying the previous fish population by 1.015, and then we're going to be subtracting off 120 fish because we're harvesting 120 fish. So we're going to do that step by step. That's going to lead us to a formula. All right, now I've got a picture of the sequence that I created in Desmos down below here, and we can see that, well, if we go along this pattern, eventually you're going to run out of fish. All right, so our goal is going to be to figure out how long that's going to take to happen. All right, and we're going to do this by building up a formula using the recursion relationship. And the initial amount was 4,000. I'm just going to plug that in here now. So it's 1.015 times 4,000 minus 120. That's after the first month. We could compute that number, all right, but it's actually going to be better for us in terms of developing a pattern to leave that in terms of the multiplications, and we're going to use some exponent notation here in a moment. Now, after the second month, you do the same thing. It's going to be 1.015, increasing by 1.5% times the previous amount, which was after the first month, minus the 120 fish you're going to harvest. Now, what we're going to do is we're going to take this expression here that we had from the previous amount, and we're going to substitute that in for F1. All right, so it's going to be 1.015 times the population of the previous months, which we just computed, minus 120. So now we're going to substitute that all in the parentheses from the previous step. So it's going to be 1.015 times 4,000 minus 120. Okay, so from here, what we're going to do is distribute this 1.015 to each one of the terms. There's 2 inside that parentheses there. All right, and just rewrite that. We'll probably go below to finish some of this calculation out. But what are we going to get here? We're going to get 1.015 times itself, so 1.015 squared times 4,000 minus 1.015 times 120 minus 120. All right, we're going to keep doing this for the F3, F4, F5 until we can figure the pattern out. All right, so let's go down below here just to give ourselves a little bit more room. All right, so after the third month, it's going to be increase the fish population by 1.5%, and then subtract off 120. All right, so after the end of the month, you're going to subtract off 120 there. All right, so now what we're going to do is we're going to take our previous result. Okay, I'm just going to write it down here. Our previous result was 1.015 squared times 4,000 minus 1.015 times 120 minus 120. We're going to take that and substitute it in for F2 here. So it'll be okay, and then we still have the subtracting of 120 there. And then the same thing's going to happen. We're going to multiply through by the 1.015 to each one of these terms. And then look at what we're coming up with. So rewriting that, we get 1.015 to the third power times 4,000 minus, multiplying that, we get 1.05 squared times 120 minus 1.015 times 120 minus 120 at the end there. Okay, let's do this one more time and then maybe we'll have the pattern figured out. So after the fourth step now, what are we going to have? The fourth month, well, the previous population is going to be increased by 1.5%. And then we'll harvest 120 fish. So we're going to substitute in for F3 what we had in our previous line here. All right, leave a lot of space there, so we got to write that out. So we're just copying that whole expression down there. And again, we could multiply this out, but for the purposes of finding a formula, it'll be better to not actually do so, to figure the pattern out. Okay, and then what we're going to go through and do is multiply the 1.015 through it again. Each of these, in this case, it's 4 terms. And let's write that out. So what do we get? F4 is going to be 1.015 to the 4th power times 4,000 minus 1.015 to the 3rd power times 120 minus 1.015 times itself, or squared, times 120 minus 1.015 times 120, and then that's the 4 terms we had by distributing through the parentheses, and then we still have the minus the 120 out there. Okay, so let's take a look at these last 2 parts here, F3 and F4. Notice what's changing in here is the subscript from 3 to 4. Okay. Where did that 3 show up? The 3 showed up as the exponent, right, of the 1.015 and then times the 4,000. The 4 subscript, again, that is the exponent there. And then what happens, we have decreasing powers on the 1.015 times 120 until we get down to 120. In the previous example, it was 2, 1 less than 3. In this step, it was 3, 1 less than 4. All right, so hopefully that's enough to help us determine what the pattern is here now. So let's write down what we would expect to get if we did this again and again and again. What would we expect to get after the nth step? It'll be 1.015 to the nth power times 4,000 minus 1.015 to the n minus first power times 120 minus the 1 less power times 120, and then we would keep on subtracting all the way down to 1.015 times 120 minus 120. Okay, now there's our formula. Right now we want to get rid of this and one thing we can do is observe that we can factor out the minus 120 from all of those. Alright, just to save a little bit of time, I'm going to do 2 steps at once. I'm going to factor out the negative 120, and then I'm going to reverse all of the terms around. So factoring that out, we would really start with 1.015 to the n minus first, and we would end with 1. I'm going to just reverse that, so it'll be 1, and then it'll be, since we factored the negatives out of all of these, it'll be plus. The next term will be 1.015 plus, and you're going to keep on getting higher and higher powers of that until you get to the last one, which will be 1.015 to the n minus first power. Okay, and what we should recognize here is that we have a finite geometric series inside this last parentheses here, which I'll just underline. Alright, so what we're going to do is apply the finite geometric series formula, which says that if we have 1 plus r squared, our common ratio, up to some given power, we'll call it p, then that's equal to 1 minus r to the p plus first power over 1 minus r. Okay, so that will allow us to get rid of the plus dot 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 and actually get a closed form expression down here for that. Alright, so let's put that in. So f sub n is going to then be just copying the first term down. Minus 120. Now we're going to apply the formula in the parentheses there, and we're going to replace that by 1 minus 1.015 to the n. In this case, what should our exponent be? Well, our previous exponent was n minus 1, so it'll be n minus 1 plus 1, all divided by 1 minus r. Alright, now the n minus 1 plus 1 is just going to be the nth power, and then we're just going to keep on simplifying this down a little bit. Alright, so we're going to just copy down again. A little bit of a tedious process here, but so you can see we're going to get a nice formula at the end of this here. Okay, minus, now I'm going to do a little bit of arithmetic here. So in the denominator, or the numerator is going to be 1 minus 1.015 to the nth power. Our denominator there would be negative 0.015. Alright, I'm going to divide that up into the negative to the minus 120. Rewrite this line once again. And if you do that division, you're going to get 8,000. Right, negative 120. We got two negatives there, so let's going to change that to addition. And then 120 divided by 0.015 comes out to exactly 8,000. And it's times 1 minus 0.015 to the nth power. Okay, now we're going to distribute the 8,000 through the parentheses there. Okay, in doing that, we get here. F sub n will be we get 8,000 minus 8,000 times 1.015 to the nth power. And then observe here that we have a couple of like terms. This term and this term both have the 1.015 to the nth power to it. Okay, so we can rewrite this then finally as 8,000, and we've got minus 8,000, negative 8,000 plus 4,000, so we get minus negative 4,000 times 1.015 to the nth power. Okay, then to finish this problem off, we're going to set that expression equal to 0, because we saw in the previously that the graph of that sequence, alright, goes down, right, and eventually it'll hit 0. Alright, so if we want to know the steady state population here, what we're going to do is set that equal to 0, right, and solve. So we want to know when is the fish population going to equal 0. Alright, so let's substitute that in there. So substitute 0 in for f sub n. Right, and then we're going to just solve this exponential equation using logarithms. So add over the 4,000 times 1.015 to the nth power term. That will then equal 8,000. Divide both sides by 4,000 to break up this multiplication, which will give us the equation 1.015 to the nth power is equal to 2. Alright, now various ways to solve this exponential equation. You could just use the definition of log base 1.015, or we could take the natural log of both sides. Right, so let's go with that second approach there. You can always use the natural log to solve these types of exponential equations, because remember, we can use the special property of logarithms that always come down in frontless factors. So then we get n times the natural log of 1.015 equals the natural log of 2. And now that's just a complicated looking linear equation, which we can now divide both sides by 1.015 to get our result. That n is equal to the natural log of 2 divided by the natural log of 1.015. And if you approximate this out, you're going to get about 46.55. And that would be years. Alright, so that'll be how long it takes for the fish population to decrease to 0.